Alright, hey guys, what's going on? So today we're going to be talking about the Louiville framework of statistical field theory. What we're going to be doing here is really establishing an understanding of something called phase space and dynamics in these things called phase spaces. And so with that being said, make sure to hit that like and subscribe button. Make sure to go into my Patreon page if you want to support the channel, which is linked below. You can also become a member if you wish to do that as well. With that being said, let's dive straight into the content. Again, also make sure to ignore the dogs. I have no way of controlling them right now. I'm trying my best to take out all their noise. If you hear them, my apologies. So we're turning to this formal development of statistical fields, right? So we talked a little bit about path integrals. We're going to revisit them later. But now we really want to understand what phase spaces are, the dynamics in these phase spaces. And so let's consider this new kind of space called phase space. And this is a very common thing that's been done in the world of modern physics. And phase space is an object identified as two coordinates, or in phase space, an object is identified as two coordinates on a position, which is a horizontal axis, which is right here, and momentum on the vertical axis. And so we can look at this picture and we can see, well, okay, we have a particle and it's changing its position a little bit as it's traveling along this trajectory, and then it turns around, it looks like, so it's going in the opposite direction now, and then it looks like it comes back to what looks like its original position. Right, so if I were to take this position here, it looks like it ends up right here. So it started here and it ended up here on the position axis. On the momentum axis, however, it really changes, right? We have this very positive momentum, and then it slows down to zero, right? So because zero is right here, and then it speeds back up, but in the opposite direction. And so we have a particle. So a trajectory in this phase space is a very conceivable trajectory that we can sort of intuit. Particles changing position and changing momentum. Suppose now we wanted to consider multiple particles. How can we do this? So if we wanted to describe a collection of particles, we need to incorporate more momentum states, because there's going to be more particles. Each particle has its own momentum. There's going to be multiple momentum states. And because they're all different particles, they need to have their own positions, different position states. This becomes a little bit difficult to understand visually, but what we can say is we have a position space and a momentum space, and together they collectively make up the entire phase space, okay? And so we can think here, okay, particle one has a position right here, particle 2 has a position here, and particle 3 has a position along this axis. Together we have a vector or a point that represents a collection of positions, right? So this is that collection of positions, n times, my apologies. I'm going to turn that volume off. So this is the collection of particles. This is n being the number of particles, and q is the point or the vector. We can make this a vector if you wanted to, but it represents a collection of positions. Similarly, we can represent a collection of momenta in this way. So doing the exact same thing, particle 1 has a momentum right here. Particle 2 has a momentum right here, and particle 3 has a momentum right here. Together they make up a vector or a point that represents a collection of momentum states. Together, big Q and big P here, they can change in time, right? But together they make the overall phase space. And so this is the phase space coordinate gamma. and it is given to us by by the collection of momentum states and the collection of position states and the collection of momentum states. This is not to be confused with the affine connection or the Christoffel symbols, even though we're using the same symbol, because it represents something completely different in general relativity. Rather, this is a symbol that denotes the entire phase space that we're considering. The dimension of this space is 2n, because for every particle there are two associated canonical variables, position and momentum. We can actually say that this is, when it really comes down to things, momentum has three components, right? X, Y, and Z components. Position has multiple components, also X, Y, and Z components. So this can actually blow up into 3n, or 3 times 2n, right? Because so you have 2n because for every particle